Hello everyone. Dual nature of radiation and matter part 1. Photoelectric effect. In this video I will be discussing mainly about photoelectric effect. First, introduction. In introduction we shall see some of the developments that have taken place in history. That is, at the end of the 19th century, experimental investigations on conduction of electricity, that is the electric discharge through gases at low pressure in a discharge tube, led to many historic discoveries. The discoveries of X-rays by Roentgen in 1895 and that of electron by J.J. Thomson in 1897 were important milestones in the understanding of the atomic structure. Cathode rays, which were discovered in 1870 by William Crookes, who suggested that these rays consisted of streams of fast-moving negatively charged particles. But the British physicist J.J. Thomson confirmed this hypothesis and also found out the value of the charge to mass ratio of these particles. J.J. Thomson is credited with the discovery of the negatively charged particle called electrons. In 1887, it was found that certain metals, when irradiated by ultraviolet light or when heated to a high temperature, were found to emit negatively charged particles. And these negatively charged particles were electrons. In 1913, the American physicist R.A. Millikan performed the pioneering oil drop experiment for the precise measurement of the charge on an electron. That is, he found that the charge on an oil droplet was always an integral multiple of an elementary charge, that is 1.602 into 10 raised to negative 19 coulomb. Millikan experiment established that electric charge is quantized. That is, it can be expressed as a multiple of the basic charge of an electron, which is 1.602 into 10 raised to negative 90. Now we can see the concept of electron emission. In the case of metals, they possess free electrons. But these free electrons are unable to escape from the surface of these metals. This is due to the attractive force of the positive ions in the metal. So electrons can escape the metal surface only if a certain minimum amount of energy is given to them. And this minimum amount of energy required is known as the work function of the metal. And work function is denoted by phi 0 and measured in electron volt. And 1 electron volt is equivalent to 1.602 into 10 raised to negative 19 joules. The work function is a property which depends on the properties and nature of the metal. The minimum energy required for electron emission can be supplied to free electron by the following ways. First is the case of thermionic emission. In this case, the energy is supplied in the form of heat. Then there is field emission, in which the energy is supplied by a strong electric field which pulls the electrons from the metal. Then the third one is the photoelectric emission, in which a light of suitable frequency is used to illuminate the metal surface, which gives sufficient energy to the electrons to escape from the surface of the metal. And these electrons are called photoelectrons. Now we can see photoelectric effect. The phenomenon of photoelectric emission was discovered in 1887 by Hertz during his electromagnetic wave experiments. Hertz observed that high voltage sparks across the detector loop were enhanced when the emitter plate was illuminated by UV light from an arc lamp. That is, light falling on a metal surface provides some electron near the surface enough energy to overcome the attraction of the positive ions in the material of the surface, and these electrons are able to escape from the surface of the metal into the surrounding space. Then the other experiment which was done to study photoelectric effect was by Halbach and Lennart during 1886 to 1902. And they experimented on negatively charged zinc plate and found that on absorbing UV light, zinc plate became neutral, losing its net positive charge, and on further absorption became negatively charged. This proved that electrons were released from the metal surface when UV radiation is incident on it. They also observed that electrons are not emitted when the frequency of light incident is less than a specific leaf value, and it was called the threshold frequency. And this frequency depends on the nature of materials used as an emitter. Some metals like zinc, magnesium, etc. emitted electrons only by absorbing UV light. But alkali metals like sodium, potassium, etc. could absorb visible radiation to emit electrons, and they are called photosensitive materials. Now we can see the experimental setup for studying the photoelectric effect. It consists of a evacuated glass tube, and the glass tube consisted of a window which was used to allow light from a monochromatic source to fall on the emitter plate, which is a metal plate. Then A is a collector plate, which is also made of metal, and a battery was used to give a potential difference between the two plates C and A. A commutator was used to switch the polarities of the charges on these two plates. A microammeter was used to measure the photoelectric current flowing in the circuit, and voltmeter was used to measure the potential difference across the two plates. Now, observations from this experiment include: first is the effect of intensity of light on photocurrent. The intensity of the monochromatic light was varied, and the measurement on the micrometer was taken, and a graph was plotted. The graph was as shown in this figure. It can be seen that the photoelectric current is directly proportional to the intensity of light. That is, the photoelectric current increased with the intensity of light. Then next is the effect of potential on photoelectric current. This is the graph showing the relation between them. At first, the emitter plate was given negative polarity while the collector was given positive polarity. At this time, when the potential was increased, the photocurrent increased and reached a certain value known as the saturation current, at which there are no more electrons to be emitted from the emitter. When the emitter is given positive and the collector is given negative, then this is known as retarding potential. In this case, the photocurrent reduced with the increase in retarding potential, and at a retarding potential negative V0, the photocurrent became 0. It was found that the saturated photocurrent increased based on intensity, as we can see in this graph, that is I3 greater than I2 greater than I1. Now you can see the effect of frequency of incident radiation on stopping potential. In this case, the same intensity of monochromatic light was used, but the frequency was varied. It can be seen that on increasing the frequency, the cutoff voltage for the retarding potential also increased. This shows that with the increase in frequency, the energy given to the electrons also increased. So this is the end of this video. In this video, I have discussed the photoelectric effect. If you have got any doubt, please comment in the section below. Thank you.